Okay, so later, uh, yeah, okay, later I will use one video. Okay, but I just want to say some last word for what we have last time. Last time we talked about the Bayesian rule, or you call it a Bayesian formula, or whatever it is. Okay. So it runs like this. Okay. So okay, well, I have some more like a theoretical or even philosophical understanding for this formula, but you only need to know how to use it for calculation. Okay, later we will talk about it. And yeah, you will see with a probability tree, right? This uh, have knowing this formula is not really necessary. You can also have different other alternative ways to make the same calculation. Okay, so just some last words because this is basically the foundation of current artificial intelligence development. Okay, typically for the two events we have in this example, okay, A and B. A is some kind of phenomenon or some of the uh, uh, belief we have. Okay, so we can call this thing belief. Okay, and this PA is the unconditional one. So we also call it prior probability. Probability. Okay, this is the formal name of this. Okay, but simply say this is basically the belief. Okay, like if this is A is the earthquake, okay, PA is our belief about how possible like within 1 year or within 10 years one earthquake will happen. Okay, so this is unconditional one, and this B is basically the data. Okay, this is what we observe from the world. Okay, like in the previous example, so A is earthquake, B is birth of normal behavior. Okay, so the important part of this formula is actually the conditional probability here. Okay, this one I can give it a very natural name. It's called likelihood. Okay, we call it a likelihood because this represents under a certain belief of a certain phenomenon. Okay, what kind of data we observe? Okay, so this is in terms of like artificial intelligence, AI, right? This is basically like um, when you train the AI, okay, you feed the AI some videos, some journal articles, okay. So when the AI they process the journal articles, they find that okay, when the title is about, for example, earthquake, and then follow up the title, there are very lengthy paragraphs talking about that birds of normal behavior. So when the AI is reading the article, okay, they build a strong likelihood of having the birds of normal behavior, and the earthquake. They build a strong estimation of this. Okay, then by combining their prior belief, okay, so before the AI read the article for the connection between this A and B, okay, they have this concept, okay, they first have this concept, okay, and then by reading a new article talking about the relationship of A and B, they update with the likelihood, okay, and that likelihood is based on the data. Okay, so what this actually implies? Okay, first thing is learning process is more like a subjective. Okay, all the kind of learning is stand with your belief. This is the common rule for any AI and the real I. Okay, real intelligence. So we say here, okay, I teach you statistics. But why I can't say teach you statistics? Because I know that you at least have graduated from high school. You know a lot of things about the society. You know how to calculate. You know how to use math. You know some of the language. You can understand me, right? And when I try to an example, things like the earthquake, you know what this is. You know what this is. Okay, so all the things you know it. I know you know. So I can build the learning process based on what you know, based on your belief. Okay, so learning is always subjective. Different people will learn different things. Okay, even though you all stay here, you listen to the same content from me, but some of you stay uh, stay around the back and watching videos. You know, very happy. Okay, never care about me. So you in your subjective learning, right? You learn something different. Okay, maybe your probability is going with some laughable content, right? That's your subjective part. Okay, so we have the belief, right? This is the root we want to build our learning, and our learning is based on some connection between data and our prior belief. That means if we estimate this wrongly, like in AI, this means we train the AI wrongly, we train the AI poorly, we may become more confused. So sometimes before you come into the classroom, you still have some sense about statistics, but comes to here because I'm bad in teaching. So you learn you heard about this and that things. Okay, a lot of things maybe just of my own interest, and then you feel so confused. What is that? I feel like I come to the university and learn a lot of confusing things. Now I don't know what is statistics. So this is also possible. Okay, it's a subjective and it do yield good or bad results depending on your linkage of data and belief. Okay, so the final part is our eventual outcome after our learning. Okay, this one is that now our belief is updated based on data. Okay, so we call this updated belief. This is how we learn. Okay, how AI learn. Okay, that's the same, everything. Okay, and in a formal way, we call this posterior probability. Okay, if you check really check some textbook regarding statistics, they will call this prior probability, call this posterior probability. Posterior means something after. Okay, something after. You first have this, then have this. Okay. Yeah, what I'm talking here is not really will not really in your exam still. I will just test whether you can calculate. Okay, whether you can use a calculation. For this thing, it will be good if you understand, as you know, what those AI scientists are doing. Okay, if you don't know, it's okay, right? Leave it there. Okay, just this is eventually it's my interest. It's what I'm really like to go with. Okay, let's just put it there. Okay, so just some last word for the Bayesian formula. So they have different names. I don't know why. So they sometimes call this Bayesian theorem. They sometimes call it Bayesian rule. Sometimes call it Bayesian formula. Okay, whatever the name they use, okay, they are referring to the same thing. Okay, later we will try to decompose this a little bit in some practical questions. So let's just see this video first. Okay, it will give us an example to apply all the thing we have here. Okay.
In this video, we're going to talk about probability trees, where we might find them useful, how we can learn our way through them. The main concept that we're going to touch on is conditional probability, and the rest of the concept is the Bayes theorem and calculated probability. Let's try this with an example. Swaziland actually happens to be the country that has the highest HIV prevalence in the world, according to 2012 estimates, 25.9% of this country's population is infected with HIV. The ELISA test is one of the first and most accurate tests for HIV. And for those who carry HIV, the ELISA test is 99.7% accurate. And for those who do not carry HIV, the test is only 92.6%. If an individual from Swaziland happens to be positive, what is the probability that he carries HIV? So this question is getting at the idea that this medical test is not 100% accurate, and therefore a patient who tests positive is not necessarily a carrier. The next question becomes, well, how likely is it that he is a carrier? When I see a question like this, and really only any word problem that seems a little wordy, the first thing you might want to think about doing is breakdown pieces. The first piece of information is about Swaziland in general. The second piece of information is about the ELISA test. And lastly, we have the actual question. Now let's try to translate these into probability speak. The first piece of information about the prevalence of HIV in Swaziland is really a marginal probability. If I am to randomly pick an individual from Swaziland, the probability that they are an HIV carrier is 0.259. The information about the accuracy of the ELISA test is not a marginal probability, but it is a conditional probability. For those who carry HIV, the ELISA test is 99.7% accurate. In other words, if I know that a person has HIV, the probability that they test positive is 0.997. On the other hand, accuracy in the case of a non-carrier really means that the test comes out negative. So the probability of a negative result, given that the person does not have HIV, is 0.926. Lastly, the question is asking us, if I know that a person has tested positive, what is the probability that they are an HIV carrier? Once again, a conditional probability. Probability of HIV given positive. What you should realize here is that earlier we were given probability, the accuracy rate of the test, and now the question that we're posed is really reversing the conditions. This is when a light bulb should come on and we should think about tree diagrams. Because tree diagrams really help us organize these pieces of information and help us work our way through the problem so that we can get at the final answer. So how do we draw a tree diagram? The first branch is always the marginal probability. If I pick a random person from Swaziland, they might be a HIV carrier, but they might not be an HIV carrier. The probability that they're an HIV carrier is 0.259. The probability that they're not is the complement of that 0.741. Now let's focus on the top branch of the tree. If a person is a carrier, one of the two things can happen when they take the ELISA test. They might test positive or they might test negative. The probability of testing positive is simply the accuracy rate of the test, 0.997. And the probability of a false negative, meaning testing negative if they are a carrier, is the complement of that probability, 0.003. Now let's move on to the bottom branch, the people who are not HIV carriers. Once again, when they take the test, one of two things can happen. They might test negative, and we know that the probability of that 0.926, this is the accuracy of the test when a person is not a carrier, and the probability of false positive, probability that they test positive if they don't have HIV, is simply the complement of that 0.074. For completeness sake, let's also mark our marginal probabilities. And in the next step, what we want to do is, what we want to think about is how can we use the probabilities that we just calculated, the marginals of the joints, to get to the conditional probability that the question is actually asking about. We're going to need to keep building on this case, so I'm going to clean up the board a little bit. These are just the probabilities that we calculated. I just got rid of the arithmetic here. Now we are coming to why did we want to actually organize this information in tree form? Well, let's say that I'm interested in finding the probability of a person being an HIV carrier and testing positive. All I have to do is follow the probabilities that I encounter on the first branch and multiply them out. You can actually do this for each one of the branches. And now let's think about why does this work? Well, let's see what I was doing in the very first branch. Probability of HIV times probability of positive given HIV is going to give us the joint probability. This is true for each one of these branches. Now let's get back to the action. What's the probability of HIV even if the person has a positive? That information is still not on the board, but we can use the piece of information that we have to get there. Now we know the person has tested positive, so they could be coming from the first branch or the third branch. And of these people who do test positive, we're really interested in the people who come from the first branch. In other words, if we want to find the probability of HIV being positive, we need to first figure out what percent of the population test positive. The sum of these two numbers, 0.2582 and 0.0548, is going to be something like 31%. And of the 31% of the population, what percent are actually HIV carriers? This is going to be a simple fraction, and that fraction happens to be 0.82. Now let's get back to the question. If an individual from Swaziland has tested positive, what is the probability that he carries HIV? This is the conditional probability that we just calculated, meaning there's an 82% chance that an individual from Swaziland who has tested positive actually carries HIV. We have gone through this problem, calculating conditional probability, but not really mentioning the Bayes theorem, even though we have explicitly used it. So now let's put these things in context in terms of Bayes. We know that generically speaking, the theorem says you want to find the probability of A and B. All you need to do is find the joint probability of A and B and divide it by the probability of B, what your condition of. Putting things in context, you want to find the probability of HIV given positive. I'm going to call HIV my event A, positive my event B. All I need to do is find the joint probability of HIV given positive and divide it by the probability that a person tests positive. Now we know that there are two types of people who test positive. Those who have HIV and those who don't have HIV, due to the fact that the test is not 100% accurate. Since people who test HIV could be coming from either of these populations, HIV and positive or HIV and negative, what I want to do is add these two joint probabilities in the denominator. Let's bring up our little probability tree to cheat off here so that we can graph the numbers. The numerator is simply the first branch, HIV and positive, and the denominators are the different probabilities from the first and third branch, getting us back to that conditional probability 0.82. I hope that this video has been useful for understanding how and when we use probability trees, how they relate to Bayes.
Okay, so it's end here. It's a bit long, I'm sorry. So because I want this to be a good foundation for us to understand what we want to do now. Okay, so yeah, just what we had before, okay? conditional probability. Okay, you have some very easy way to get it from the contingency table by seeing a specific row or column. Okay, depending on your problem. Okay, here. Okay. Right. So what I want to have here is one similar example. Okay, just similar to the Switzerland example. So this is about breast cancer. So first, we have seen some estimation for the breast cancer for all women. So the probability is about 1.7%. Okay, not very high, but still significant for people to draw some attention. Okay, so then we have some way to test for it. Okay, which is very convenient. Okay, so this is called the mammography. So the mammography says that if you do have the breast cancer, around 78% of those who really have the cancer can be detected. Okay, so that's the first thing. So second thing is that in some articles, right, they actually criticize that this mammogram can yield up to 10% false positive. So they may actually test the one with without cancer and have a positive result for them. So it actually creates some trouble. Okay. So this is from the those researcher developer scientist perspective. They develop these scientists. Okay, they do find some patients, right? They already confirmed that having the cancer, right? And they try to collect the probability data here. But those are basically reported by those scientists, developers, right? For us, whether this mammograms can be improved or sufficient, right? That's not really our concern, right? For us, we don't really care about those specific data, but we care about that. What if I suspect, not me, right? So what if we suspect that we may have this kind of cancer, and we go to the hospital, and then the doctor may let us do the mammogram. And what if the mammogram says I'm positive, and to what extent that we should worry about that we really have the cancer, right? So we care about that. Okay, if we as a patient, if we really do this test and get the positive, how much we should worry about, right? Yeah, because if we really confirm that we have cancer, right, we need to take a lot of treatment, right? Sometimes the treatment are even detrimental, right? The treatment maybe sometimes let you eat chemicals, like let you have the radioactive treatments. Sometimes the cancer didn't kill you, but the severe treatment do kill you mostly. Right? So it's quite a risky decision. So we want to make our decision as precise, as accurate as possible. So to us, the question turns to be, if we go to make a test, and how possible could we have this cancer? Okay, we can try to split this question a little bit. I write it in this way. So the first branch of the probability tree is always the fact, the belief there, right? So it's about some phenomenon, okay? So this phenomenon is about the cancer, okay? So we have the cancer or have no cancer. It says, right, 1.7% of individuals of women in the US, or maybe almost all of the world, they have the cancer. So we can take the complementary part. Okay, 983, right here. So there's someone should be without cancer. So then for the mammogram, okay, we apply the test. Okay, just simply say we apply the test. So for the one really with cancer, we have two possible case. Okay, so the first possible case is that we correctly identify the one with cancer. Okay, in the previous description, we have the probability for it. And there are some cases that we have the false negative. That means we fail to detect the cancer, although the patient really have the problem. Okay, this should be the complementary of the positive case. Okay, anyway, as long as you take the test, you will anyway get a positive or negative, right? So 2. Okay. And for those without cancer, right, still there are some cases that is false positive. So although you are healthy, but you don't know what kind of reason happens, but you are tested in a false positive, right? We have seen some kind of news about that, you know. Some people are false tested positive for cancer, and they spend all their money, and by the end, the doctor says, okay, this is actually a wrong test, right? It's actually a false positive, right? So we have some kind of news about that, right? So the false positive is at most 10%, 0.1, and false negative 0.9. So we have those numbers, but precisely we have some meaning for those numbers. Okay, here for the cancer, no cancer here, this is the marginal probability, right? Unconditional probability, or you can say. So this is a P cancer, right? This is a P no cancer. And for the true positive, false positive here, they are all conditional on the case, conditional on the with cancer case or the without cancer case, right? So here for this true positive case, this 0.78 is actually a conditional probability, which actually shows positive under the person really have cancer. Okay, so following here is a P negative and the person without cancer. Okay, so come back to our concerns. So as a patient, what I want to know, okay, I don't care those technical issues. I don't care. But if I'm the patient, I want to know that if I go to the hospital, I make the test, and the test is positive, how much I should worry about the cancer, right? So to me, my question is, if I'm positive, what is the probability that I really have the cancer? Right. So this one can be decomposed, right, into a ratio. So the ratio here is that you should know the probability for this intersection. That is, you both have the cancer and you also test positive, divided by the case that all the case that you are positive. Okay, include the false positive and the true positive. So what you should see is the P cancer and divided by P cancer and positive plus P no cancer. Okay. So basically we just want to know this number and this number, right? This one the same, right? We want to know these two numbers. So we have marginal probability, joint conditional probability. So we can definitely use the definition for conditional probability to see the joint probability, right? So we just multiply these two. So what we should do is to multiply these two, okay? The P positive and cancer, right? This is the good case, right? True positive. We should have 0.0133. So this is a negative case, okay? False negative, but this is not what we are concerning, right? So 0.0037. So, and the next is positive and no cancer. Okay, this is some confusing cases, right? That makes our trust to the test lower. Okay, that is also the case we really want us to be, right? So this should be 0.0983, and finally here is 0.8847, right? This one is basically the majority, right? Because only a few person have the cancer, right? Less than 2%. And for those without cancer, in 90% probability they will have the correct positive negative case. Okay, this one is the majority. Okay, so we list all the joint probability here for these two events, right? So first event is a test result. Second event is whether the person exactly has the cancer. Okay, so each result have two outcome, right? And we list four outcome in total here. We are actually covering all possible outcome, right? So that's actually why it's very natural for us to observe that if we sum up all the four possibility here, sum up them together, we will see one, right? Because we already cover all possible outcomes, right? And if we want to say, if we want to take say some sample regarding the breast cancer and the test, okay, this should be our sample space, right? Including all the four possible outcome regarding the two two variables we are caring about. Okay, so put the numbers into it. Okay, now we have all the required numbers. Cancer positive. So cancer positive, no cancer positive, so false positive case. So 0.0133 plus 0.0983. So yeah, without the final result, we will see that this rate should be very low. This is 0.09, this is 0.01. Okay, this one should be very low. So it's actually about 12%. So that means what? That means given all the conditions, all the descriptions here, all the knowledge for the effectiveness of this test, as well as the population of breast cancer, even if the patient made this test once and get positive, still for the patient to really have the cancer, right? The probability is not very high, 12% only. And that's why, you know, if you go to the hospital, sometimes for some tests, once you run it, the doctors saw the result. The doctor say, "Oh, It's a bad news, but it cannot really confirm any evidence. Right? It's just very suggestive. Okay, the case is here. Okay, if you let me try to explain this a little bit, that is because the population who truly have this cancer is actually, in terms of number, it's actually very small. Okay, less than 2%. That makes even you have a good method to test. Like even if you change this to like 99%, this number will be still very small. And on the other hand, because the majority of individuals in the society actually have no cancer, and even if your false positive rate is very low, this rate will be relatively high because you have this in your product. Okay, so that makes eventually the power of your test is not that trustworthy. Okay, this now at least you can understand here, right? Okay, try to make it more complicated. Okay, so yeah, before we talk about the more complicated case, okay, let's first ask one simple question. So if one patient go to have this test and find a positive result, well, definitely she worried about that. She would worry about that. So probably she want to take it again to see. Maybe the first time the test is wrong. They just because of some randomness, I got a positive result. I should be okay. Right? Everyone should have kind of this kind of thought. Right? It's very natural, understandable. So here okay, we want to ask a very small question. Okay, very quick question. That is. Regardless of all others, okay? We just want to see the second test, okay? For the second test, what is the probability for the specific women to have the cancer if we test it for positive? Yeah, so I told you this is actually a very simple question. So although we list all the numbers here, okay, this is a very simple question. So the number is exactly the same as before. Okay, because what we are asking here is that just for this second test, what is the power of this test? How much we can trust this test? Okay, if the test is conducted accordingly, you run it for one round or run it for another one round, the power of true positive, power of true negative, false positive should be the same. Okay, the situation should be the same for the second round of tests. Okay, because this test is kind of objective there. Okay, it will not be true if like your first time you get the positive result and in the second test, in some magical way that your first time result will impact your second time. Okay, they run independently every time the tests are new, right? There will be a new round of tests. So you talk about the second round, you are exactly talking about the same thing like the first round. Okay, even if you do this again and again and again, okay, you do it for 10 times, 100 times, the 100th time, you still have this 12%. Oh, this first sounds like a bad news, right? Like we did it once, it's not really trustworthy. It only gives us 12% possibility. And if we do it twice, the second one also give us the 12% probability. Then what is the point to repeat that? Okay, it's like seems like meaningless for us to do this test at all, because we do it once, it won't prove anything. We do it twice, it does not make anything different. Well, that's not really the case, because if you really do the second round, your situation change here. When you start your first round of test, what is your consideration? Your consideration is based on the data, based on the prediction of what kind of institution. Okay, they predict that 1.7% of individuals in the will have the breast cancer. This is the foundation for you to make all the probability inference, right? You do like a detect, right? You have this information, so that by the end you have your inference here. But if you already get a positive result at the first round, then at least for your case, you are not one of the public right now, okay? You are one of here. That means for you, if you build the probability tree for yourself, who already test positive once, your first branch of the tree should be 12% here and 88% here. Because now you have the result from first round, okay? This is your first test result. This is based on all citizens. Okay? And then you do the second round. Well, for your second round, the power is still the same. The power of this test, as long as you are doing the same test, the power should be the same. So you still have 78% probability to get a positive, true positive. Okay? You still have the same probability to get false positive. You still have the 10% for false positive. You still have the 90% to have the false negative. Well, under this case, your four possible outcome have different joint probability now, right? Your first interaction, positive, and you already have the cancer, now should be 0.0936, right? It's much, much larger, right? So we can do the calculation again and again, negative and cancer. So 0.1 to 0.22, we have 0.0264. So similarly, false positive, no cancer. Zero 0.88, 0.1, so 0.088. Right, so then 0.792, right? Okay, so now I can have some new conditional probability, which is the probability that this person really have cancer, and we have second positive, first round positive. Okay. So first round positive here, because we take it as given. Okay, we take it as given. This happens like that. It happens like that. Okay. In that case, what we want to have is the joint probability for having cancer and the second round result. Okay. Okay, cancer, second test result positive, 0.0936. Okay, and in the denominator, we covered all case that will make the second round positive. Okay, given the first round is positive. So in that case, we have the false positive case and the true positive case. We have 0.0936 plus 0.088. Okay, result considering about result, I already know this number by the end, this ratio should be more than 50, right? Because now this part is larger than this part, right? I can sense that this one is definitely more than 50. So we will by the end have the result here, 0.52. Okay, so you see the magical part, right? You see the magical part. That means, although for one round of the test, due to its nature that it can only test 78 true positive case and will have 10% false, up to 10% false positive for no cancer case. Okay, by the end, if we try to infer the possibility that a tested positive person would really have the cancer, right? When we try to make this inference, the possibility is actually very low. But this does not mean this test is meaningless, is useless, right? Instead, for this kind of test, as long as this test is easy enough to be conduct, we can update our belief by using the first round test result and then rerun the test again, repeat the same process, although this repeating should have same true positive possibility, false positive possibility, but because we update our belief here, so now the power of this test is very well improved. Okay, now at least we have more than 50% confidence that, okay, after these two rounds of tests, like if we flip a coin now for the destiny of this patient, this patient will have more than half possibility to really have the cancer because we tested for 2 rounds. Although we start from a very low number here, as the nature of this cancer is quite rare in terms of the total population. Okay, this is the whole game. Okay. So the probability tree here in the slides, we also call this process as to calculate the invert probability. Because here, right, for this 0.78, this is like positive and the cancer, and by the end you want to calculate the cancer and the positive, so like we invert the condition, right? So we sometimes also call it inverted probability. Well, but actually you can see the theory is actually meaningful, right, in our real life, as well as long as you also understand that the second round there, okay, it will be very okay. Well, so in the textbook or okay, in the slides here, you will see a version of this Bayesian theorem run like that. Okay, don't be panicked, like don't be confused. That is just a variation of this. Okay, this is the easiest way, right? This because I want to use it to establish the so-called learning process. Okay, just slightly vary this a little bit, you will get this formula. Okay, here the case is that we changed A and B a little bit. So now we change A and B as test result. Okay, so B we just call it test positive. Okay, because then the complementary of B is test negative. Okay, anyway, as long as you take the test, you have 2 results. So for A, we specifically say A have A1, which is have cancer, and A2, which is no cancer. Okay, so in that case, the theorem we have can be changed in that way, right? So A1, you have cancer. This is exactly P cancer and the positive result, okay? So what you have here is A1 and B. Okay, so for A1 and B, it should equals to B and A1 multiply A1 and divided by PB. Right, so comparing to this case, we just change A to A1, or we just change the notation a little, nothing else. Okay, so just an additional variation is that we know that A1 and A2 covers all possible outcome for variable A. Okay, so we can decompose PB to two parts. So PB can be decomposed into P A1 and B plus P A2 and B. Okay, so this is like if you draw a graph. So this graph is basically separated by A1 and A2 UI. So as this, if this graph is representing all the population, okay, then A1 is those population with cancer, A2 is all the population without cancer. Okay, well, I'm not really making it so quantitative. It's more like a qualitative way to show the result. Okay, and within this whole population, okay, all people, we can have the case for those all people test positive. So this part is A1 and B, right? And this part is A2 and B. So, well, from this picture, you can easily see that if we add A1 and B with A2 and A2 and B, we will just have PB, right? Understandable, right? And a further variation is, okay, we try to write the joint probability in terms of conditional probability. Okay, that leads to the case like PBA1 multiply PA1 plus PBA2 multiply PA2. Okay, right. So if you take this part, and this part, right, you have the formula here, right? Nothing else. So write it very simply. It is just this. Okay, just to match with the problem we have here. Okay, you can decompose it into this way. By the end, the concept is just like this. Okay, not that much. All right. So the theorem is not that hard. Okay. In concept, it is just a natural description for learning process. But just for a specific question we have, right, we can slightly twist it based on mathematical rules so that it fits our problem, okay? Right, you can see that here, what you did here is just to calculate the PB on A1, right? PB on A1 is this, right? Multiply with A1, and then PB on A2, this is the false positive 0.1 here, multiply with PA2, 0.983 here, okay? Sum these two together, and take the true positive as your numerator, you have this 1, okay? And I think the great point for this process is this process really describe the learning process, right? So if you are the person, you never if you are the woman there, you are the person, you never do any kind of test. So you probably have a sense about yourself that okay, the probability for me to have this kind of cancer is 1.7%. That is based on the data provided by the institution. Then you go to make this test first time, and unfortunately, it makes a positive, right? This positive result update your belief. Previously, your belief is that I'm just one of the population. I'm just one of those individuals in the Earth on the Earth in this planet. But now because you made something, you collect the data, you update your belief. Now for you, okay, you know that now you are definitely not one of them. You are about having 12% to have the cancer. Okay? And this learning process can be sequential because after the first round, you update your belief and you can add up new data points by retest with the mammogram. And now your probability to have the cancer turns to be more than half. You can even repeat it infinitely. You can do it for the third time and update this probability to here. Okay, you will have something different. Okay, you can do it for 4, 5, 6, 10 times. As long as you repeat the test for enough rounds, you will improve the belief of your status, right? So that's also why, if you go to the hospital, when the doctor asks you to do some kind of test, and then they saw the test, okay. If you want to further investigate whether you really have this, right? Perhaps very likely the doctor will ask you, okay, maybe 2 or 3 months later, you can redo the test, okay, to see the results. And that's why later if you go to work, okay, usually you will have your annual health screening, okay, to test this and that issues. Okay, if consecutively in maybe 3 years, you have some abnormal result for a certain testable threshold, testable maybe genes, maybe some specific target. Okay, if you have the positive or abnormal result for that thing for 3 years, your doctor may ask you to have specific treatment for it. But if you just have it occasionally once, and the next year you don't have it, the doctor will very likely tell you, okay, it's not likely to be the case. Okay, you don't need to worry about it. Okay, right. So you see those statistical theories. It built up our society in this way. Okay. So here is another case regarding epidemiological model. Okay, it's called SIR model. Basically, it just changed the probability tree a little bit. Okay, by split the people into 3 groups. Okay, that's also I will just quickly go through this. Okay, so because I guess you are more or less familiar with this SIR model much more, as this is exactly the model for the government to guess how much people were infected by the COVID-19, right? So this is what we just had several years ago. So okay, so they try to divide people into three groups. Okay, so susceptible, that means you can be infected in the future, but now you are healthy. Okay, infected means, yeah, now you are infected, you are in problem. Okay, recovered means you previously got infected, but now you are good. Okay, you are in good health. So for a specific test, right? This test can, let's say, they can show a very good accuracy for the pure good case and the pure bad case. Okay, for the susceptible case, the correct negative case is 95%. For the infected case, the correct true positive case should be about 99%. Okay, but only for the recovered case, the test may have some problem. Okay, they will have the correct negative for 0.65 only. Okay, so with this distribution, we can do the same stuff. We can do the same stuff like we have here. Okay, for a simple person, what they care about is that what if we have the test and then we can say we are really positive. Okay, so if we run this calculation a little bit, we will see that actually the probability for really test to really test the true case is not really high. Okay, so if in this case 10% of the population got infected, this is not small. Okay, not small, right? This is really fundamental. You think about it, 1 of 10 people are infected, and they're coughing, right, because of COVID-19. This is actually a very large amount already. And the test, we cannot say the test is really powerless because the correctness for this test for susceptible and infected is really high, 95, 99, right? Although it is less accurate with the recovered case, but well, we do have some limitation, right? We do have some limitation. There's no perfect treatment. Even with the case here, right? Even with the case here, we can see that a person tested positive who should be really infected. Here the chance is just 0.423. Okay. Right. So that's, you think about that. That's why, through the years with COVID-19, right? They use a swab into your nose, use a swab into your throat. And even if someone tests positive, they try to quarantine those first tested positive. But even you are quarantined, they will still try to use a swab to test you for multiple times. Why? Why? They test you positive, they just quarantine you. There should be no more work. Why after they quarantine you into the hotel, into somewhere, and they still throughout the first several days, they go to test you, they go to torture you with swabs for several more times. Right, that is because they also need to run this belief updating process, right? The first test, once they put the swab into your nose, they find, oh, you may have perhaps a 50% probability to have the COVID-19. So as long as we have the power, right, we quarantine all of you, okay, and put each of you into separate rooms, okay, for safety, because we may definitely know that there are some false positive there. And then throughout the first few days, okay, day 1, day 2, day 3, they still test you, okay, they still torture you with that small swab. And then if you consecutively test for positive, they keep updating their belief. You are now, then after 3 days, okay, the possibility for you to have 4 plus sign, 4 positive sign, and really have the COVID-19 will be like more than 99% eventually. That's how they really confirm your case is correct, right? So I think we have 5 more minutes. We talk about the sampling issue a little bit. Okay, so here, the issue here also we have many slides. But the question is, or the problem is very simple. I just tell you the conclusion in maybe 2 minutes. Okay, so sampling, if we will do the sampling many times, not just one time you sampled all the necessary observation, but we might do the sampling for many times. The problem here is that we could do the multiple round of sampling with 2 different ways. One is called with replacement, the other one is called without replacement. With replacement means after the first round, you pull out some sample, some observations, you put it back and do your second round. So basically, this makes your population remains the same at the beginning of your second round. So your second round is exactly in the same situation as your first round. So the result of your second round should be independent of your first round. Okay, so in this very easy case, like if you have a bag with 10 chips, 5 red, 3 blue, 2 orange, and you do the sampling with replacement, so by putting it back. So if your first time draw for the chance for your first time to draw a blue chip is 0.3, 30%. Then the probability for that you have the blue chip in the first round and also have the blue chip in the second round, okay, taking this as a conditional probability rather than a drawing probability, you will see your probability is still 0.3. So by observe this, that means no matter no matter what you have in your first round, it won't affect the result of your second round. So that means your draws are independent. Okay, any new round is just a freshly new round. Okay, but instead, if you do without replacement, you think that okay, I already see, I have already seen this kind of observations. Okay, next time I want to see something new. Okay, I don't want to see those observations anymore. Okay, in that case, you are doing the sampling without replacement. That will make the draws dependent. Okay, because as you make your first draw, you change the population, and your second draw will lose some possibility. Okay, like if you first draw from the 10 chips, you have the blue chip. Then if you don't put it back in your second draw, right, you have only 9 choices, and the probability for you to draw the blue chip again is just 2/9. Okay, so now you have the sampling without replacement that is not independent. Okay, that will be important if your sample is small, but that will be less important if your sample is large enough, because if you are not talking about 10 chips, but 1 million chips, okay, replace or without replacement, and it doesn't matter. Okay, so okay, 1 more minute. Let's talk about random variables. We will have another more class next week to talk about how to utilize the expectation and variance with random variables. But now I just take a very, very brief introduction of it. Okay, basically a random variable is just a pure mathematical way for us to show the random process. Okay, we define random process loosely. Okay, we just say random process is some kind of process that we know all possible outcome, but we don't know which outcome will certainly comes out. Here, the random variable is just try to show it mathematically. Okay, we define this variable as big X, and any outcome of this big X as a small x. So that is how we try to mathematically show them. Okay. Yeah, I think it is the time. So I will go back to the office, change my clothes a little bit, and then see you guys in the Slack 301. Okay. Our lab do not require you to use your own laptop, but if you want to install the R in your own laptop, you can bring your laptop there. Okay, in the first class, I will tell you how to install it. It's very easy. Okay, so see you there. I will start by 4 p.m. Okay, so take your time. Yeah, that's it.